This lecture is going to introduce projectiles. Specifically, we are going to talk about just horizontal projectiles. In the next video, we'll talk about projectiles that are launched up in the air at some sort of angle. So just to start us thinking about projectiles and about the motion in a projectile, let me just ask you this scenario, okay? There's a zookeeper, and he wants to shoot a banana at Curious George, who's high up in a tree. But as soon as George sees the banana coming, he curiously lets go of the branch to catch it. Now, in order for George to catch the banana on his way down, should the zookeeper A, aim above George, B, aim right at George, or C, aim slightly below George? So just think about an answer real quick on your head, in your head, drop it down on a sheet of paper, and we'll come back and answer this question in just a sec. All right. The bullet dilemma is a common dilemma that we talk about in physics when we start to learn about projectiles. And the bullet dilemma is that if someone were standing and they had a gun and they were in an open field where there was nothing that the bullet would hit, okay? And let's say they had one bullet in their hand and they had one bullet in the gun. If they were to shoot the gun and drop the bullet simultaneously, then both of the bullets would actually hit each other, or would hit the ground at exactly the same time, okay? Which is sort of counterintuitive. The bullet coming from the gun is going to fly really far in the horizontal direction, but it's still going to take the same amount of time to strike the ground as the one that you have dropped from the same height from your hand. So motion is independent, okay? The rate at which you fall is not affected by how fast you're traveling in the horizontal direction. So even though a bullet is traveling extremely fast, how long it takes to fall to the earth is not affected by that horizontal motion, okay? Horizontal motion does not affect vertical motion whatsoever. They are completely independent of one another, okay? The only thing that links the two is time, and that's how we're going to solve for different parts of the problem, okay? Now, if we think about vertical motion and time, how long it takes for something to fall to the ground, the only thing that affects that is gravity, so we can calculate that fairly easily, okay? So what's the answer? The answer is that you would aim directly at George, because the bullet, or the banana, sorry, that you were shooting at George, we don't want to kill George, the banana that we were shooting at George would fall at the same rate as George himself fell, okay? If you aimed above, it would go over his head. If you aim below, then it would be too low for him to catch. Alright, so horizontal projectiles. If we look at some vectors that demonstrate a projectile that's shot horizontally off the top of a cliff, okay? So here's the cliff, and the little purple ball here is shot in the x direction with some velocity v, okay? Oop. As it travels, you can see that all of the velocity vectors stay exactly the same in the x direction. It's not slowing down, and this is assuming that we are ignoring air resistance, right? But you can see that the velocity vector in the y direction begins to increase, and that's because there's something causing it to accelerate, which is gravity. There is absolutely no acceleration in the x direction. Alright, so some things that we need to note for horizontal projectiles before I give you a sample problem. The initial velocity in the y direction is equal to 0 because you're shooting it straight in the horizontal x direction. So in the y-axis, we can just treat it as if it's being dropped straight off the cliff rather than being launched out. In the x-axis direction, we're moving with a constant velocity, so there is no acceleration, okay? Horizontal motion in the x direction has a constant speed, so that's really important to remember. Vertical motion is going to be constantly accelerating due to gravity, Okay, so let's do a sample problem where we make some sort of calculations. Okay, so let's say you're sent to investigate an incident where a car has plummeted from the top of the cliff. The officer asked if you can tell how fast the car was traveling. We measured the cliff height, and we know that the cliff is 66 meters high. And we measured the distance of the car from the base of the cliff to where it landed. So it's 90 meters away from the base of the cliff. Okay? So now we want to find out how fast the car was going. Okay? So let's go ahead and do this problem. Alright, so I'm going to draw a picture. Okay? So I have a cliff here, and I know that the car is going to have some initial velocity in this direction, okay? And I'm going to say that velocity initial x. Actually, you know what? I'm not even going to put initial there because we know that the x is constant the whole time. So we'll just say velocity x in that direction. My cliff was 66 meters high, and where it landed was over here, 90 meters away, okay? So this 66 meters represents my displacement in the y direction. The 90 meters represents my displacement in the x direction. Okay? So the first thing that I want to solve for, because I mentioned that this is what links the two. Okay? What links the two is time. Okay? So I want to figure out how long that car was in the air, right? And in order to do this, I'm going to treat it like a dropping problem, because remember, another thing that I know besides what is given here, I have some assumptions that I can make. I know that my velocity initial in the y direction is 0 meters per second, okay? And I also know that gravity is my acceleration. It's negative 10 meters per second squared. Okay? So I'm trying to find time, and I have acceleration, I have initial velocity, and I have displacement, right? Now, it's important to note, gravity is negative 10 meters per second squared, and because we're saying that we start from here and we fall down the cliff, we're actually going to say that the displacement is negative 66 meters, okay? So in order to solve for the time, given these variables, this is the equation that I have. I've got d in the y direction is equal to v initial in the y direction times t plus 1/2 at squared. Okay. Now what's important to note is whenever your velocity is, or your initial velocity is 0, this term cancels out. Okay. So we really end up with the equation dy equals 1/2 at squared. Okay. So let's plug in our numbers. We have negative 66 meters is equal to 1/2 times negative 10 meters per second squared, t squared. Okay? And if I plug that into my calculator, I get 66 divided by 5, and then square root gives me 3.63 seconds. So my time is equal to 3.63 seconds. Okay? So the time that it takes to fall is also the time that it takes to fly this direction, okay? Now the next part is really easy because we know that the velocity is constant. So we don't need to use one of these constant acceleration equations because we're not accelerating at all, okay? So here I can just say that Vx is equal to displacement in the x direction over time, okay? And of course, the question was, let me slide that up a little bit. Of course, our original question was, what was this velocity? So we're going to have to algebraically solve that. Oh, wait, no, never mind. We already have it solved for us. So now we just have to plug and chug, right? So 90 meters over 3.63 seconds. And I get that my V initial is equal to 24.8 about meters per second. Okay, so for every projectile problem, you really want to try and find time by using the y direction, and then use the time in the x to solve for whatever you're trying to solve for. Okay, let's do one more quick one. Alright, in this problem it says, let me click to the next slide. It'll let me. Danger Jan wants to jump from the top of a building into a swimming pool that's located 10 meters from the edge of the building. If the building is 37 meters high, and if Dan's top speed is 3 meters per second, then would he make it? So we got 10 meters away in a 37 meter building. Okay, so let's go ahead and do this one. Okay, again, I'm going to start by drawing. Okay, so here is my building. dy is equal to negative 37 meters, because that's how far he's going to fall. Vx is 3 meters per second. This time I know it. And the target, it's not really drawn to scale. Well, my pool is right here, and that is 10 meters away, and that is my dx. Okay, so again, I'm going to begin by solving for time, because time is what links them. Okay, I know that my v initial y is equal to 0, so I can just skip ahead to this dy equals 1/2 at squared. Then plug in my numbers. Negative 37 equals 1/2 times negative 10 for gravity, t squared. 37 divided by 5, square root. It's going to be in the air for 2.72 seconds. Okay? Now, this is also the time in the x direction. So I have Vx equals dx over t. And this time, I'm trying to figure out if he can go 10 meters, right? Hopefully he can make it 10 meters, otherwise we have killed Danger Dan, right? So let's take our initial velocity, Vx, multiply by t, and that will give us how far he actually jumps. Okay, so now just plug and chug. 3 meters per second times 2.72 seconds gives us 8.16 meters, right? So we would say that Danger Dan is going to splat right there before the pool. Okay. Go back over these and watch me do them again. Just to review, we'll be doing a few practice problems in class, and in the next lecture we will cover projectiles that are launched at an angle.